Hello, we are Team 23092, Short-Term Aerial Reconnaissance, or STAR for short, sponsored by Raytheon. In today's day and age, there is a need for a low-cost, lightweight, aerial reconnaissance device that is easily deployable by ground forces on demand in an operational area. The STAR system will serve as a fixed surveillance camera to gain rapid situational awareness and monitor a first responder's hazardous situation. Our solution is a drone that is inexpensive, has the ability to be deployed quickly by Border Patrol, sheriff departments, and local police departments, and is nearly completely autonomous once launched. This intelligence, surveillance, reconnaissance device will be launched at a high loft angle out of a user's pneumatic launcher, hover for no longer than 5 minutes, and broadcast live video.
STAR uses a wide field of view camera, providing a high-resolution video of the operational area with the capability of distinguishing between objects as small as 6 inches in length. A handheld device will receive and display data from the STAR drone. The camera range is determined by camera and receiver capabilities. The focus of our project is to design, build, and test each critical subsystem of the STAR device. We have boiled this down to 5 main subsystems: launch slug, arm deployment, camera, autopilot, and battery spread bench. We will now go into further detail about each of these subsystems, starting with the launch slug.
The first subsystem, a slug prototype, must be able to withstand the launch loads of a pneumatic launcher and reach a predetermined altitude. This prototype is designed using SolidWorks computer automated design software and built with 3D printed nylon material to keep it lightweight, easily producible, and low cost. The design of this olive round was done with ease of use and sturdiness in mind. Several analyses were required to ensure that the design would be able to withstand high forces, launch and fly with stability through the air, and stay within a reasonable weight to ensure hovering was possible. SolidWorks software was used to find the center of gravity of the object with all anticipated parts and pieces at the time of launch assembled. The software was also used to run a stress analysis to find that the model could undergo well over the PSI required to reach 100 meters. Several slug prototypes were iteratively tested, first by dropping from varied distances multiple times. The drop test is detailed in Mill Standard 810G.
The test identifies weak points in the design that can be fixed with proper packaging and small tweaks in the fastening design. Finally, our prototype will be launched from a true pneumatic launcher, showing that it can survive high launch loads and fly with stability through the air. Moving on to our next subsystem, the camera. A camera subsystem with a receiver tests and verifies the range that a chosen camera can distinguish 6 inches of object, and shows that the camera can transmit video feed to a user's device. The most challenging component of the subsystem was finding a camera and receiver that can transmit and receive high-resolution picture respectively.
Our first iteration of testing yielded images that were extremely grainy, showing that from barely 10 yards away, a 6-inch object isn't even picked up by the camera. This is how we determined our issue with camera and receiver compatibility. Our final choice in camera is digital, has a 14mm diameter lens and a resolution of 720p. A transmitter will send the camera feed to the receiver, which is also digital, and is a device that the user can watch the video feed from.
These chosen devices show a clearer picture than our first round of testing. However, technological options for cameras of this size significantly limit how much resolution we can get. 6-inch objects can be distinguished from 10 to 15 yards away. From farther away, the user can still distinguish a person's clothing and other characteristics, as well as locate landmarks, making this device still extremely useful for gaining situational awareness. A separate subsystem will verify the hovering and autopilot requirements. This subsystem will include a separate frame with motors, propellers, battery power, flight controller module, and camera.
Similar to the slug subsystem, the hovering and autopilot subsystem required several iterations of prototyping. The first prototype consisted of a basic frame, a flight controller setup. The purpose of this was to learn how to use our chosen autopilot software, Betaflight. Autopilot capabilities proved to be one of the largest risks in this project. So prototyping the hovering subsystem early was crucial for risk mitigation. Later prototyping incorporated all other components of the quadcopter. First onto another simple frame to see how the components interact together, then onto the slug prototype with the arms extended. Stability when hovering was another risk and concern in this subsystem, as the camera must transmit clear and stable video to the user. Incorporating the camera into our prototypes early helped to reduce the risk of stability becoming a larger issue.
The static arm deployment is modeled using 3D printed prototype parts and demonstrates the mechanics of the spring-loaded arms as they exit the pneumatic launcher, as well as the power-on sequence as the batteries are engaged and the motors power on. These arms were first designed using SolidWorks, then 3D printed with nylon and carbon fiber. They are protected on the slug prototype by a sabot, which peels off the device once it is launched.
The final verification of the arms show a static model of the arms deployment using carbon fiber arms attached to a slug prototype and spring-loaded. The motors and batteries are integrated into the test and are switched on once the arms deploy, showing that the interface between battery power and arms deployment is quick and simple. While making the drone power on transition autonomously is outside of our project scope, our work on the subsystem has simplified the design challenges for future years to work through. Finally, a battery spread bench models the system's capability to provide enough power to hover for 5 minutes.
This subsystem depends on the weight analysis of our all-up round, as well as an analysis of the motor power outage and battery capacity. The total weight of the all-up round with the components is 360 grams. Each of the 4 motors are capable of producing up to 165 grams of thrust. Finally, the batteries had to be chosen to accommodate the motors and weight as well as other constraints, including the 40 millimeter diameter size. We're using 4 14500 batteries, and a battery pack was soldered together to fit inside the slug prototype. All of the battery power components were wired together and tested by timing how long it took the battery pack to stop producing enough power to allow the device to hover.
This verification test showed that the batteries will provide enough power to hover for about 6.5 minutes before showing signs of low battery. Testing while hovering in outdoor conditions is outside of our project scope. However, having a surplus of hover time will allow for the device to also spend battery power overcoming wind effects. Designing, prototyping, analyzing, and testing of each of the STAR subsystems required ordering parts that were relatively specialized, which made lead times and off-the-counter product availability a large risk. This was mitigated by keeping a detailed parts list, designating one person to be in charge of ordering parts well in advance of needing them, and finding parts that have high stock.
Our project scope required us to design, build, test, and verify the requirements for each of the 5 subsystems discussed in this video. Moving forward, future teams will be required to fully integrate these subsystems into one nearly autonomous system. The largest challenges that future teams will have is timing the arm deployment to occur at the most effective point in the flight trajectory once the device is launched, getting the battery to power up the motors at the correct time without user input, and getting the device to capture mid-flight and begin a stable hover. Ensuring that all components fit inside of the sabot will also be a challenge for future teams, as well as furthering the autopilot capabilities to stay on station even in wind and inclement weather. The path forward for a more tactical design will be having access to a 5-axis CNC machine to machine a more robust frame and form factoring all electronics to optimize performance that will fit inside the 40 millimeter outer mold line.
Our additional work on integrating some of the subsystems of the STAR device, such as getting the 40 millimeter all-up round to hover, will eliminate a portion of integration that future teams will be required to do. The short-term area reconnaissance project has significant implications for gaining rapid situational awareness in situations that are quickly developing and potentially dangerous. This device could save lives. By allowing first responders to quickly deploy the device and view what's going on, they can identify dangerous assailants and objects that can help themselves and others avoid areas of high risk without physically entering these areas first. We would like to thank our sponsor Raytheon for giving us the opportunity to work on this project and our mentor for providing us with advice and guidance throughout this experience. Thank you.